the talk by Ilia Gaiur. As usual, you see the title, so Ilia, you are welcome. Please.
Yeah, thank you, Joseph. Today I'm going to do a very simple talk about Hamiltonian reduction and with some focus on the Calogero-Moser systems. Before I will start, I want to do a very short overview of the things I'm going to speak about today. So in a nutshell, what I'm going to talk about is the Noether theorem, but I would say the, let's say, symplectic version of the Noether theorem. And as classically, Noether theorem says that we have the following correspondence. So if we have some dynamical system over, say, Hamiltonian system, but even dynamical system, there is a mantra that symmetries are the first integrals. And this means that if you have some symmetry in your system, you can reduce degrees of freedom by resolving these first integrals. But when I first saw this theorem, I definitely understood the content of this theorem, but I didn't really understand how to use it explicitly. And in a sense, this what I call symplectic version, or better say the moment map theory, is a very explicit version of the Noether theorem, and it has a very big it has a very I would say such theory, the moment map theory, can be used in different contexts, and it's not only about Hamiltonian system, but there are a big bunch of geometrical problems where you use this theory. But today I will speak only about mechanical systems, Hamiltonian systems. And my slogan for today is to show you that somehow in some examples, we have the following a slogan that we start with some trivial big system, and here big means a lot of degrees of freedom. And then using the Noether theorem and explicitly having Hamiltonian reduction, we reduce such system to something, let's say, smaller, but non-trivial. And the key example I'm going to talk about today is rational Calogero-Moser system, or maybe we also can speak about trigonometric, but let's see, which is just n particle Hamiltonian system with the following Hamiltonian. Which is known to be integrable, and I think it was so Calogero found this. He was studying some quantum mechanical systems, quantum mechanical potentials, which are integrable in the sense that he can compute the spectrum. But what I want to show you today is that such system may be seen as the reduction of free particle system which is written on the cotangent bundle to GLN, where you can see that the number of particles here corresponds to the rank of my general linear algebra. Or if you want to do compact, you can also, or real and compact, you can also consider this as the system on.
Sorry, in the first formula, there's absolute value of Qi minus Qg in denominator, or not?
Sorry, it's square.
Oh, okay.
Yes, sorry. This was a misprint. Yeah, so yeah, okay. So yeah, if you want to do kind of real and compact, you consider T star to SUN, but it doesn't make any sense in my talk. Well, and in general, I want to speak about the Hamiltonian reduction or symplectic reduction, and show you this example and some more example. And before I start to speak about this general theory, I just want to show you the scheme, or better say ingredients of the Hamiltonian reduction. So the first thing is that we start with some symplectic manifold with the group action. So we take some Lie group which acts on this manifold by symplectomorphisms. And if this action is good enough, I will explain what means good. It means that, so, well, if action is good, then we will show that there is a map from manifold to the dual of the Lie algebra of the group G, which also sends the, I will call it G orbits in M to the coadjoint orbits of the Lie algebra G. And then I will, well, when you have such action and you are lucky to compute moment map, or not lucky, you just compute it, you can easily show that the moment map gives first integrals for any Hamiltonian system with Hamiltonian to be invariant function of the G action. So I will use the following notation. So it's a global function on M, which is G invariant. Okay.
Ilya, a question. This mu that sends M to G star, it preserves symplectic structures.
Sorry, in the red line, what is
Yes, yes.
O star? G orbits to what O star? What is O star?
O star is coadjoint orbit.
Oh,
So, Ilya, it possesses Kirillov symplectic structure, yes?
Yes. Indeed.
And we have symplectic structure on M, yes?
Yes.
Does mu preserve the structures?
Not really. So
Not really, okay.
the key point here is that well, I'm going to speak about this, but let me say that there are some. So you have to choose a level set of moment map. So the standard. Okay, let me use another slide. So the standard theorem. Let me formulate it then. So well.
Sorry, and what is O of M in the previous? The last. What is O of M?
It's the algebra of global functions, globally defined functions.
Or global. What OMG? What is it?
Yeah. So we have a lot of functions on M, and G means that the functions which are invariant with respect to G action. Well, the standard notation for this is the following. And it's the, I would say, canonical ring, right? If you do algebraic geometry. And but because of the coadjoint orbits, I use O instead of this symbol because this mat call O usually used for adjoint and coadjoint orbits. Yeah, but again, the ingredients are the following. So you have a symplectic manifold with group action on it by symplectomorphisms. Then you can construct, if this action is good enough, I mean, I will explain what means good and how to do the reduction. Then you can construct so-called moment map. And this moment map will provide you first integrals for any system which is invariant under such action. Joseph, I didn't answer your question, I think, right? Yeah.
That not necessary.
But I will say the following. So usually we consider the pre-image of zero, and the theorem by Mars and Weinstein says that if you will quotient pre-image of zero by G action, you can write down the symplectic form starting from the initial symplectic form on your symplectic manifold M, and writing down the reduced form on the on this quotient space. Okay.
Okay.
Yeah. Okay. And so okay. Just to finish this scheme. So after we do this, we have some Hamiltonian system. We have some reduced space. We have a bunch of first integrals. Yeah, integrals here. And then we just perform a reduction with respect to this first integrals. And in particular, I'm sorry, can you see what I'm writing now?
No.
No. The picture doesn't change.
Okay, let me restart sharing. I'm sorry for that. Okay, now you can see a little bit more. And when I'm doing this, you also can see. Okay, so if at some point you will not see me writing, please tell me, because sometimes my tablet fails to synchronize with computer. Okay, so yeah, then we perform a reduction with respect to these first integrals, and well, you can think about this as a standard reduction in Hamiltonian mechanics. Okay.
We have problems.
Yeah, I see. Yeah, I'm so sorry. Usually everything works well.
Not now. We see you.
I'm so sorry. Oh, now you can see.
Yes.
Okay. Great. So now it should work fine. All right. So again, let me continue. So now let me explain you. Let me explain you this part of the scheme. I think the most mysterious, the moment map theory, and give you a few examples. And well, see how it will go. But I want to ask you if I need to remind you some things about the constant Kirillov-Suryo symplectic form and Lie-Poisson bracket on the Lie dual to the Lie algebras.
Yes, I think you do.
Yeah. Okay. So okay, this will call say coadjoint orbits, Lie-Poisson, and constant Kirillov-Suryo. So, well, I will write it for any group, but you may think about the matrix groups. It's much easier because then you can imagine the coadjoint orbit and coadjoint action. So I start with some Lie group G. It's Lie algebra small g, which is T at identity to G. And the I think the main object is a Lie coalgebra, which is just which is not an algebra actually, but it's just a dual to G. So it's just a space of linear maps from G to some field K. So it's just C. Yeah, and I think one of the greatest thing about the dual Lie algebra is that dual to Lie algebra is that actually, if I will take the space of functions on the dual algebra, it is a Poisson algebra. So there is a Poisson bracket, which is skew, which has Jacobi identity and also is derivation. And how we introduce this Poisson bracket for the functions on the dual algebra, dual of Lie algebra. So we do the following. So take any function from G star to field K. Then the differential of this map definitely is a linear function on G star by definition of differential. Then it means that since df is a linear function, it means that df for any function f is in the Lie algebra itself. And then Lie-Poisson bracket is given by, so you take two function f and g from O of G star, and since so it's a Poisson algebra, so it means that I take two functions and I obtain another function on the G star, and I want to evaluate this function at some element of G star I call theta. And then such evaluation, right, in the following way. So I take the commutator of the differentials of my maps at point theta, both of them. So I take the commutator because these things are in the Lie algebra. I know what is commutator for df and dg, and then I just do the pairing with the element from G star because this thing, the commutator, lives in Lie algebra, and this theta lives in G star. And then because of the skew properties of the commutator, Jacobi identity, and all this stuff, and because we do differential, we can easily prove that such bracket is indeed Poisson bracket. And well, so it proves that the space of functions, the canonical ring, is a Poisson algebra. So let me just give the most simple example. So let me consider algebra SL2, and we know that SL2 is isomorphic to the dual to SL2 is isomorphic to SL2 because of the existence of Killing form on SL2 and the pairing between the algebra and coalgebra given by the trace function. So if I take theta from SL2 star and x from SL2, the pairing is given by trace of theta multiplied by x. Yeah, because both of them are matrix algebras, I can definitely define a product of two matrices and then I take a trace. And now let me consider a general element in SL2, which is just traceless matrix. And well, again, since SL2 and SL2 star are the same, I do not differ between these two objects. And now I want to consider the following functions. So f of h of a gives me h, f of e of a gives me e, and f of small f of a gives me small f. And these functions are definitely linear, and moreover, they can be written as traces of product with some basis of SL2. So if I want to have h, for example, it's just a trace of 1, 0, 0, 1 divided by 2 multiplied by a. If I want to get e, I just take trace of 0, 0, 1, 0 with a. And if I want to have f, I just take trace of 0, 1, 0, 0, a. And these are the functions.
Sorry, the first line something strange because you multiply the scalar matrix to a, but trace of a is 0 by the trace of a minus.
Thank you. Yes, I'm sorry. Yes, that's true. So yeah, we have this set of functions. You can also prove that all polynomial functions are generated by these functions. I think it's quite obvious. And moreover, you can see that actually the differential of these maps are linear. So the differentials coincide with the matrices I wrote here. And now, if I want to compute the Poisson bracket between, for example, FH and FE, evaluated at point A, what I do is I just take trace of A multiplied by 1 minus 1, 0 divided by 2 with 0, 0, 1, 0. And if you will compute it, you will obtain that this thing equals to E, and you obtain f of E at point A. And well, if you will do this for other elements, you will get that f of h with f of f gives you minus f, and f of e with f of f gives you 2f of h up to sign, maybe minus in front. I don't really remember. And you see that actually when we computed this Poisson structure for the functions on the contingent or on the Lie coalgebra, it looks very similar to initial algebra. And the thing is that actually, when you consider Lie Poisson bracket, in some sense, you just take the structure constants of your Lie algebra and leave them up to the space of the functions. Well, in a sense, by just taking the space of linear functions and then generate the whole ring. But you take the structure constants for this basis of the linear functions from the Lie algebra. And well, the main question here is, okay, this is a Poisson space, but what are the symplectic leaves of this Poisson structure? And I think this theorem by Kostant, Kirillov, and Suryo, I don't remember how to write his surname correctly, so I will keep it like this. And theorem states that that coadjoint orbits are symplectic leaves which actually means the following, that if you take the coadjoint action on G star, then invariant functions are Casimirs. And we can easily check this in the case of SL2, because in the case of SL2, the coadjoint action of the group is given by the conjugation. So G minus 1 A G. And then when in SL2, the invariant functions of the conjugation are always eigenvalues, or here you have only one eigenvalue because you have 2 times 2 traceless matrix, and you even can encode this eigenvalue in determinant of A. And determinant may be seen as the following function. So you take f of h squared plus f of e f of f with minus in front, I guess. And you can easily check that this thing indeed commutes with all the generators of your Poisson algebra. So this is not a proof, but this is just evidence of the of this theorem. But in general, yeah. So theorem states that coadjoint orbits are symplectic leaves. Okay.
Sorry, what it means? Invariant functions are Casimirs. What it means really?
It means that it means the following. So you have okay, you have your O of G star with Poisson bracket. You have some ideal generated by functions which are invariant. So you have adjoint G star of x equals to f of x. Okay. And if you take any function from I, so let G in I, okay, G is not okay, H in I, then it means that H commutes with anything. I mean, here I can take any function f from here. Okay.
Thank you.
Yeah. Yeah. So yeah, and it's usual thing. Yeah, when you have some Poisson algebra, how to find symplectic leaf? You just find the all Casimirs, fix them, and this gives you a symplectic leaf. Yeah, okay. And well, and in principle for SL2, you can even write down the Darboux coordinates because, well, in SL2 case, we have that the coadjoint orbits are given by the algebraic variety of the following form. So you have 3 generators and the following conic equation for them. And since
probably FF, I mean FF, not FH.
But FF, yes. I
And
even
what's the
write,
theta? It is the definition of theta.
Theta is just a constant, right?
Because on leaves, constant on leaves.
Yeah. Now I fix the leaf, right? Or even let's use just theta, not theta squared. It's constant. And you can see that for SL2, if you will draw these leaves, so it's theta. When theta is 0, you have a very special leaf, which is nilpotent cone, and it's singular. And actually here you have 2 coadjoint orbits. The one is 0, which is closed, and this is just stationary point of the action, and all other is the open orbit of the nilpotent element 0, 1, 0, 0. And if theta is positive, I guess you have, well, this is a real picture, of course. You have something like this. And when theta is less than 0, you have some hyperbolas, I guess. Yeah, well, in case of SL2, of course, your coadjoint orbits, they are topologically trivial because they are given by conic equation in 3 variable. And you can even write down the Darboux coordinates for this symplectic leaf. And for SL2, this Darboux parameterization is given by the following parameterization. Yeah. But in principle, you may have something more complicated, and this is a big problem to write down. First of all, Darboux parameterization of your coadjoint orbit if you deal with some more complicated algebras. At least I don't know how to do this. On the other hand, if geometrically your coadjoint orbit is not trivial, it means that Darboux coordinates is not enough, because Darboux coordinates is just a differential geometric patching, right? You cannot see any invariance of your coadjoint orbit writing down Darboux coordinates. Nevertheless, sometimes it's very important to have an opportunity to write down these Darboux coordinates, and today I will do some examples where we will compute Darboux coordinates and obtain some very interesting from the integrable system point of view Hamiltonians. But we should keep in mind that in general, these things are a bit more complicated than just T star to Rn. In that case, it's just T star to R2. Okay, so why do I need this coadjoint orbit stuff? Because in the theory of the moment map, coadjoint orbits play a key role. And now, if you don't have a question, if you don't have any questions about this part, I will continue. But if you have, please ask them so we can go further. Okay. So, okay, symplectic quotients. So as I told you in the beginning, so it will be symplectic quotient and Hamiltonian reduction. So as I told you in the beginning, we start with some symplectic manifold with the group G, Lie group, acting on this symplectic manifold via symplectomorphisms. Well, maybe you want to require this group to be compact. Let's forget about it for a while. Let's just, well, if you want anything from this group, you may assume that this group is good enough to fit your expectations. Yeah, so, well, let me write down what means act by symplectomorphism. So for any element from group G, we have a map G of X. We can act on any point in M and obtain another point in M. And the thing is that the pullback of this map preserves symplectic form. Then another important thing about such group action, so it's symplectic group action. Another thing I want to require is that G acts in a Hamiltonian way. What does it mean? So it means the following. So when we have a group acting on the manifold, we always have that we can send its Lie algebra G to the vector fields on manifold. How do we do this? So we take any element X from Lie algebra, then we construct the element in the group using exponent map. Oh, sorry. So it will be in the group. Yeah, okay. Let me. So we take E of Tx, which is in the group, and then the vector field, which corresponds to element X in the Lie algebra at point P, is defined as d over dt E Tx acting on P at t equals to 0. And then well, in general, why we love symplectic manifolds, because when we have symplectic form, we usually can say if the, first of all, we can transfer all vector fields to one forms, and we can define Hamiltonian flows. So Hamiltonian group action means that for any element in Lie algebra of your group, the corresponding vector fields Vx are Hamiltonian. So it means that omega of V of x, so when we insert the vector field in the symplectic form, this form is closed. So there is a function h which depends on the element in the Lie algebra x, and such thing equals to the differential of h of x. You can, so okay, so group acts in a Hamiltonian way means that all the vector fields generated by this group action are Hamiltonian. You may also prove that these Hamiltonians are linear. So it means that if you will take two elements from the Lie algebra, the Hamiltonian which will correspond to the sum of these elements will be sum of the Hamiltonians. And it means that actually this H of X may be defined as the pairing of X with something, well, at each point of our manifold, and this something, or better say, the dual to the Hamiltonian of the vector field in the Lie algebra, is called moment map. So let me write it as a definition.
So this is, Ilya, sorry,
Mhm.
this is the same mu that you mentioned in the beginning, yes?
Right. Yes.
Okay. Okay, thanks.
Yes. So let me write it as a definition. So moment map is the dual in terms of Lie group and dual Lie group to the Hamiltonians given by vector fields of group action. And what you can prove is that this is, I think this is a theorem. I don't, well, I mean, not very complicated theorem, is that mu commutes with G invariant functions. Proof is quite easy. First of all, let me take h of x. This is definitely a function on my manifold because it's defined for any point. And take f to be invariant, G invariant function. When I compute the Poisson bracket with Hamiltonian, it's the same as to compute the Lie derivative with respect to the vector field, which corresponds to this function. But since f is G invariant, it's 0. On the other hand, we know that h of x is given by the pairing of the moment map with vector field x, or with, not with vector field x, but with element of the Lie algebra x. And this element, in a sense, is a constant, it's arbitrary element. So it means that here I can switch the brackets, and this thing equals to pairing of the Poisson bracket of mu with f, and you pair it with x. But since x is now, I didn't specify x, so it's an arbitrary element of my Lie algebra. It means that the pairing equals to 0 only if the element from the dual is 0. Okay. And we see that in case when we have, for example, G symmetry of our symplectic manifold and G invariant Hamiltonian, moment map gives us automatically the set of first integrals. Why I say that this is the set? Because since mu is in G star, it means that it's an element of the vector space, so it has, well, a lot of components, right? So let me do a very simple example. Let me consider Cn with the following symplectic form. Well, I think it's standard symplectic form. dzi wedge, dzi bar. And let me consider the action by nth power of u1. And this action is, so u1 is just, each copy is just complex numbers, which are, which modulus is 1. and the action is given by zi goes to zi ti, where ti corresponds to each copy of u1 in this direct product. Then such action is definitely symplectic, because if I take dzi wedge dzi bar, then it goes to ti bar, dzi wedge dzi bar, and by definition of u1 it is just 1, right? And now I want to compute the moment map. So how do I do this? In principle, what could I do is I should consider the vector field generated by this action, and these vector fields are quite well, they are just, for example, if I act by only T1, vector field is just Z1 over D over ds equals to Z1 and so on. Yeah, but what I didn't say is the following. So when you have Liouville form on your symplectic manifold, so in our case, for example, omega is given by differential of the one form, I from 1 to n, zi dzi bar. Then it's much easier to find the moment map. What I mean is that you can even insert your vector field into the Liouville form, and you don't need to, well, okay, so let's forget about it for a while. Yeah, so what if you will take the vector fields which are generated by this action and insert them into the symplectic form, you will find that actually each time you insert each vector field, you get that this the result is the following, that your I'm sorry.
Factors of I, maybe you've forgotten.
Sorry?
Maybe you've forgotten factors of I, which maybe would be helpful. Maybe they can help to add factors of I. Množitelí I.
No. Sorry. Yeah, I'm sorry. I a bit sorry, I a little bit messed up all this stuff, but let me consider even more simple example when I consider only U1 action on Cn. So I don't have any, yeah, exactly. So I have only one T and I act by the following way. So then it's easy to compute that the moment map will be given by the following formula. So you just take Z1 squared plus Z2 squared and so on, Zn squared. Well, probably plus any constant lambda. And you see that moment map, the violation with respect to the level set of the moment map gives you the spheres in Cn in a sense. Okay, so this was an example. I didn't compute it properly, but let me skip it for this example. So this is an example definitely of the symplectic action, and you can check that this gives you a moment map of this action explicitly. Okay, and before stating the main result in the moment map theory and the Hamiltonian reduction theory, I want to assume that my action is or will be equivariant. So, and I just give a definition of equivariant moment map. So moment map is called equivariant if the following diagram commutes. So you have your symplectic manifold M, and you have a map to G star given by the moment map. Then you have the group acting on this M. So I have for any element of my Lie group, I have a map which sends M to itself. And then I can again apply the moment map to M and obtain G star. And here I use the adjoint action with respect to G minus 1, the co-adjoint action. So we call moment map to be, we say that moment map is equivariant if such diagram commutes. And what does it mean? It means that actually equivariance means that G orbit of P in M goes to the co-adjoint orbit of the mu of P. And in particular, for example, it means that if I take the level, the zero set of the moment map, so if I take mu minus 1 over 0, then the Lie group G acts on it. So this is also, this will be also a, well, I would say something with G action, right? Because if my moment map of point P is 0, then the co-adjoint orbit of 0 is 0, obviously, and it means that mu of G of P is also 0, right? And the theorem about the symplectic reduction by the Marsden and Weinstein tells us the following. So let M omega be a Hamiltonian G space, which means that there is a G action which is Hamiltonian and symplectic, obviously, with moment map mu. Then if G acts on mu minus 1 of 0 freely and properly, then firstly mu minus 1 quotient by G action is a manifold. Secondly, there is a projection of mu minus 1 of 0 is a manifold, sorry, called M reduced. Secondly, we have a map from mu minus 1 of 0 to M reduced, and this is a principal G bundle. And moreover, M reduced is a symplectic manifold, and the symplectic form is given by the following equation. So we have the embedding of preimage of 0 into M, and if we will take the pullback of the symplectic form with respect to this embedding I, it should be the same as the pullback of the projection of this G bundle. So because we have a P from mu minus 1 to M reduced, and if we assume that there is some symplectic form, then I can take a pullback of it, and I will obtain, and I will get the 2 form on mu minus 1 of 0, and this is how we defined omega reduced. Okay, so in particular, what Marsden-Weinstein theorem says is that when we have the when we have a good group action by symplectomorphism with the moment map, then we can do the reduction with respect to 0 locus of this moment map. And when we will perform such reduction, we will obtain again symplectic manifold. So in case if you had some Hamiltonian dynamics on your initial manifold, which is also invariant under this group action, so it's not just a symmetry of your manifold, but is also a symmetry of your Hamiltonian system, then you can reduce it to this reduced space, because you will still have Hamiltonian, and you will still have symplectic form. The thing is that in general, we want to consider not only 0 moment maps, but the non-trivial sets of the moment map. And then there is a theorem by, again, Marsden-Weinstein and Mayer, which allows to pass from the 0 set of the moment map to any set of the moment map. But the problem will be is that you have to deal with also coadjoint action on the level set of the moment map. And well, in particular, it requires some work. And I actually wanted to ask how many time do I have since now? And do I have 30 minutes or less? Yosef?
Yeah, I always forget to switch on the microphone. Yes, you have 30 minutes for sure, but you may feel yourself free until 9 o'clock Moscow time.
Okay.
Actually, you have 41 minutes.
Yeah, okay. Well, let me try to switch. But what I want to say is that actually this theorem, this theory may be extended even not only for the 0 locuses of the moment maps, but to something non-trivial. But let me try to give you an example and then discuss this extension, because I think now I'm too abstract to be understandable, but maybe not. So, okay, let me now consider the main example I wanted to show you. The main example is T star 2 GLN, and this space definitely is the same as GLN cross GLN. So we have 2 matrices P and Q, which are both in GLN, and well, since it's a tangent bundle, definitely it is a symplectic manifold, and symplectic form is given by the following well, construction. So you take the differential of your matrix P, differential of your matrix Q, then you perform a matrix multiplication, but with wedge instead of multiplication, and you take a trace. But if you want to write it down in the coordinates, you can easily do this. So it will be dPij wedge dQji. sum over I and j from 1 to n. And now I want to introduce the following action. So I will take group GLN and we'll perform the and we'll consider the following action. So if I have a pair P and Q and element G from GLN, then this action writes as G minus 1 P G G minus 1 Q G. Well, you can easily check that this action is symplectic because if you will insert this into the symplectic form, you will get here G minus 1 dP G wedge G minus 1 dQ G. So here, since G and G minus 1, since G and G minus 1 are the constant matrices, you may ignore the wedge sign, so they just cancel each other and give you identity. And the external ones cancels each other because of the fact that the race is invariant under the cyclic permutation, right? So you definitely have a symplectic action here. Okay, and now I want to consider free particle system, which means that I will take the following Hamiltonian, which is just a generalization of the
cotangent left of adjoint action of GLN on its Lie algebra.
Sorry, can you repeat, please?
Is this the cotangent left of the adjoint action of GLN on its Lie algebra?
Yes, yes, I think so. Yes, definitely.
Okay, I see. Thank you.
Well, I don't cotangent left.
So I mean,
yeah, I understand. Yeah, maybe.
That's automatically symplectic. Is that right? Yeah.
Yeah, I don't know. Yeah, probably. Yeah. So yeah, and now I just want to consider the following Hamiltonian system here, which is just a kind of the free particle. So we can easily see that the system writes in the following way. So P dot will give you 0 with respect to this Hamiltonian, because we see that P commutes with itself in a sense, yeah. So definitely such Hamiltonian gives trivial dynamic on P, and for Q, it should give you P. Okay. Yeah, because you can easily check it in the coordinates, right? Because yeah, because each Qij has non-trivial bracket only with Gi. It gives you, sorry, not 0 but 1, right? And then you have just a trace of so when you compute Q dot with Hamiltonian, it's just a trace of E Gi with P divided by 2. Well, not divided by 2 actually, just trace of EGIP, and it gives you just Pij. This is just linear algebra. So this is a very simple system, and you can easily solve it because you know that P is just a constant matrix along the flow of your Hamiltonian system. And then you just integrate this constant matrix, you obtain something linear in T plus some constants which are defined by the Cauchy data. So this system is extremely easy, right? But on the other hand, we see that the symplectic manifold itself has this symmetry, and you can easily check that the Hamiltonian is invariant by such action because you have a trace of p square, so it will be just a function of eigenvalues, so it's invariant under the conjugation, right? So we can try to perform the reduction with respect to this action, and what should we do? Firstly, we should compute the moment map. So let's try to do this. So so to do this, I will use the Liouville form because this is cotangent bundle, and symplectic form is always given by the derivative of the differential of the Liouville form. So Liouville form here is just trace of QP dp, right? And for each element, so let me take G equals to E in power of Tx. The vector field, which is corresponds to such action, is the following. So it will be, okay, let me write it in the coordinates. So it will be d over dp ij of commutator of x with p ij plus commutator of x and q ij d over dq ij. Okay, up to sign, but the important thing is that sign is the same in both cases. Then when I want to just insert this vector field in my Liouville form, what I obtain is the following. So since Liouville form doesn't depend on dq, so I can ignore this part of the symplectic form, obviously. So I don't need it. Or not symplectic form, I'm sorry, of the vector field. And now when if I want to insert this stuff here, so what do I have? This Liouville form is written as Qij dp gi, and this will be sum over, okay, here I have a sum over I and j, obviously, from 1 to n, and here I have sum from I, j, from 1 to n, of Qij with x, p, but now since I have gi here, I should write gi here also, right? And we can easily see that this is just the trace of q with x and p. And again, we can use the properties of trace, its cyclic invariance, and what we obtain is that actually this is the same as the trace of x with commutator of q and p with minus in front, I guess. Okay, and here we definitely see that I take any vector field, I insert it into Liouville form. Well, okay, I mean, I can take derivative and insert it into the, well, since it's Liouville form, definitely this will be the Hamiltonian for the vector field Vx, right? And we, moreover, can see that this Hamiltonian is given as the pairing between the commutator of Q and P and the vector field, the element of the Lie algebra which generates the vector field. So this thing will be a moment map for it will be a moment map for our for our action. And well, one more sanity check. So as I told you, this is a moment map, but I also told you that moment map gives you first integral for any Hamiltonian which is invariant under this action. And we have precisely this situation. We have invariant Hamiltonian, we have this moment map. Okay, let's check if moment map is if moment map commutes with this Hamiltonian, and it's very easy because if I take derivative with respect to t and the dynamics given by p dot equals to 0, q dot equals to 0 or equals to p, sorry, then d mu is just q dot with p plus q p dot, right? And this is automatically 0 because p dot is 0. And this thing is just p with p, and it's also 0. So what we were thinking, that what we are getting here, right? And now the question is how to perform the final reduction. And let me firstly consider very trivial example. As I told you, Marsden-Weisstein theory says that, well, actually, if you have a moment map, you should take the pre-image of 0 and do the reduction with respect to group action. So you quotient by the group G. What does it mean here? It means that actually you consider such set of matrices Q and P which commute. It means that there is a basis in which both Q and P are diagonal, right? And since I have this quotient by the group action, I can consider my system up to conjugation by any matrix. And if I will choose such matrix, it means that I can choose it to be the transition matrix to the eigenbasis of Q and P. And what I obtain is that actually here in such space, my Hamiltonian will be just a trace of diagonal matrix, so P1 Pn squared divided by 2. And actually I have no, there is nothing interesting here because my Hamiltonian becomes just a free particle, but n free particles. And so yes, so in this situation we cannot obtain any interesting. The second example, which is a little bit more, which is much more complicated, is to take mu to be arbitrary. Then you obtain a very big system, and let me discuss it later. Because in this example, what you will obtain, I will write down the reduced Hamiltonian, you will obtain so-called spin Calogero system. So it looks like the standard Calogero system, but here you have Sij, Sgk, Gi, where these functions, these elements are called spin variables. And they have no trivial Poisson bracket with itself. Well, it actually, they will have a constant Kirillov-Suryaud, well, Lie Poisson bracket, which is just given by constant Kirillov-Suryaud symplectic form on the reduced space. Well, and there is an intermediate situation when you choose moment map to be the following very special matrix. So you take the identity matrix, you take the rank 1 matrix out of it of the following form, and you can multiply it by any scalar, constant scalar in front. And this is what people usually refer as Hamiltonian reduction, and it was introduced by I think Kostant, Kazhdan, and Steinberg. Correct me if I'm wrong. And the thing is that why this case is so interesting is the following, that in such situation, you obtain non-trivial system, but still you have a very big stabilizer of your moment map. So you can reduce to n degrees of freedom. Because in principle, what could we have is the following. So the dimension of our initial phase space, T star to GLN, sorry, is just n squared multiplied by 2, right? Then when you perform the Hamiltonian reduction, you obtain that you have a moment map, Q and P, which gives you additionally, well, let's say n multiplied by n minus 1. Why I call this? Because the trace of the commutator is 0, right? But you have n multiplied by n minus 1 additional first integral. Right? And if you will just naively do the reduction as you do in Hamiltonian system, the dimension of the reduced space, T star of GLM, should be what? It should be, you take initial dimension 2n squared and you take out of it the number of first integrals twice, right? Because you always have, you think about first integrals as the action variables, but you can always find the angle variables, and that's how you take n minus 1 degrees of freedom, but in the language of the dimensions, you take 2n minus 1. And this is not 2n in general, right? Well, you can consider some particular n, but in general, it's not. So what's so special about this moment map? Let me just try to perform this reduction and show you how it can be done by hands. Sorry? Okay, I'll continue. So what we have is that now we have two matrices Q and P, which commutator is 1 minus this matrix 1, 1, 1, tensor 1, 1, 1, 1. So this is just a rank 1 matrix of the following form. You have at each entry you have 1, right? Now I fix it and I want to resolve it, but I also want to conjugate by the group action, so I can perform the following conjugation. So let me switch to the eigenbasis of the matrix Q, for example. So what I mean is that I will conjugate all the moment map equation by G, which gives me G minus 1 Q G equals to X, which is just diagonal matrix Q1 till Qn. I don't want to consider any non-semi-simple case here. And that then what I will have is the following. So here I will have some X, here I will have some Y, which is just a conjugation of P by the same matrix, G minus 1 PG. And on the right-hand side, sorry, G is not very good. Let me use kappa here for my coupling constant. Okay, doesn't matter. And on the right-hand side, what I will have is the following. So identity matrix will not, well, it will stay the same, because when you conjugate identity matrix, you have identity, you get identity matrix. But the rank 1 matrix may change. But the only thing that we know is that it's still rank 1 matrix. So you multiply by these matrices, these vectors, and what you obtain is that here you have some A1, A2, AN, and you multiply it by B1, B2, Bn. All right. Well, in principle, this A and B's can be arbitrary, but on the other hand, what we know is that on the left-hand side, we obtain the commutator with diagonal matrix Q1 till Qn. But the commutator with diagonal matrix always has zeros on diagonals, right? It can be checked. Well, it can be checked by hands, and you have something here. And what it means that these elements A and these elements B are non-arbitrary, but we have that AI are equals to BI in power of -1, right? So now here, instead of just B's, we have A1 -1, A2 -1, and so on, AN -1. And the next step is to do and the next step you can do is that you can consider additionally gauge by the stabilizer of diagonal matrix. So you can consider the conjugation by other diagonal matrices, and if you will consider conjugation by the following matrix, so you have here A1, A2, AN. Such gauge or such conjugation will bring your system to the following form. So on the right-hand side, you will still have X and Y twiddle, some matrix, and on the left-hand side and on the right-hand side, you will have the same value of the moment map. So in principle, what could we obtain is that actually this is just an element of the coadjoint orbit of the initial moment map. But since the stabilizer of this matrix is very, very big, it can be, you can always diagonalize one of your initial matrices Q and P and keep the moment map the same. So keep it to be constant. Because when we choose moment map initially, we could choose it as a constant matrix, but then when you do this conjugation, you may lose this property of to be constant, because you, in general, conjugate by the non-constant matrix, because this X, for example, is the this Q is some matrix which depends on the which depends on the variable, which depends on the coordinates of your symplectic manifold. So everything can happen, right? And finally, what you obtain is that you just need to resolve the following equation.
Kappa, Ilia, kappa.
Kappa, yes, thank you. Kappa. And if you will resolve it with diagonal X, so it's diagonal X1, Xn, you will get that Y twiddle is given by the following matrix. So you cannot define its diagonal entries, and you use them as the coordinates, because when you do the commutator with diagonal matrix, you always have that diagonal goes to 0. It's a kernel of the adjoint map. And here on the off-diagonal elements, you will have that each element has the following form. It's I kappa divided by Qi minus Qj. And if you're familiar with integrable systems theory, you will identify this matrix as a lax matrix of Calogero-Moser system. And then inserting this matrix into your Hamiltonian, because it was invariant, right? So trace doesn't change under the conjugation, you will get the Calogero-Moser Hamiltonian. Kappa square, Qi minus Qj square. And you may ask me, what about integrability? But easily for the unreduced system, you can check that actually such elements commute, and it means that actually you obtain a very classical result that the integrals of motion for integrable system with Lax matrix are given by the traces of the power or the well, spectral invariance, whatever. And you can always also see after performing this reduction that the equation for Y-Twiddle becomes of the Lax form. I don't really remember what I should put here, but there is some M matrix here, right? Yeah, but this happened because again, we choose we decided to pick a very special moment map with a very special I would say we don't pick very special moment map, but that's what we do. But we pick very special coadjoint orbit, because coadjoint orbit of this element is very small, and it gives an opportunity to reduce a lot of degrees of freedom, because we ended up with 2n with dimension 2n, right? And but in principle we had to have a bigger dimension. And well, let me try to explain what happens when we consider an arbitrary coadjoint orbit. So, for example, if I choose mu to be in the coadjoint orbit of some element, I don't know, x, then I cannot perform, well, I can try to perform the same scheme, but how can I fit this scheme into the Marsden-Weinstein theory in the Marsden-Weinstein reduction?
Yes, so sorry, I don't understand. Mu is the momentum map, or it is now something different?
It's a momentum map, right?
But it is a map from our M to G star, and how mu of at some point.
Yeah. Sorry.
Just to understand.
Yeah.
Okay.
You're absolutely right. So mu is a map from M to G star, right? But when I was telling you about equivariant moment maps, and in this example, you can check it by hand, and in general, you check that your moment map is equivariant by hands. I told you that it sends G orbit to the coadjoint orbit, right?
Yeah.
So let me take an element. Let me take some, let me take some arbitrary point of my manifold, okay?
Mm-hmm.
Mu of P can be anything, right?
Yeah.
I don't know what it is. But then let me consider the coadjoint orbit of mu of P.
Mm-hmm.
And now I construct the following, I do the following construction. Let me, since this thing is symplectic manifold, I can construct the following direct product. I take my initial symplectic manifold and take the coadjoint orbit of mu of P. Okay?
Mm-hmm.
And here I have omega to be symplectic form, and here I have, let's say, constant Kirillov sur U. symplectic form, right? Such direct product is also symplectic manifold, and actually there is a big amount of different symplectic form, because if I will take the following symplectic form here, plus lambda 2 omega kks. What I mean here is that actually from this space I have a projection map to M, and I have projection map to O star of mu of P. And this means that I take the pullback of projection 1, and here I take a pullback of projection 2, right? A very simple theorem is that if lambda 1 and lambda 2 are in C star square, then this defines you symplectic form, right? And now I say, okay, let me consider very special symplectic form and consider lambda 1 to be 1 and lambda 2 to be -1. So I will have omega star minus omega kks star. All right? Yes. Okay.
Yes.
Yeah. The next step is the following. So I think this is not.
So are these the pullbacks of the omega ks? You pull them back to the product space and then do the linear combination. Is that correct?
Yes. So you have projection 1 and projection 2, and yeah, of course, I should write down here projection 1 star of omega, and here I should. Okay.
Thank you.
And imagine for a second that both of these symplectic manifolds are Hamiltonian G spaces with its own moment maps. Then this product will be also Hamiltonian G space, and the moment map here, let me call it mu big, is just moment map from here, so my standard mu, minus, let me call it moment map of constant Kirillov-Suryo form. Okay? Yosef?
Yes.
Okay, cool. And the one of the greatest things that I have no time to explain, and I didn't suppose to, is that when you consider the coadjoint orbit of some element, then the moment map just sends your coadjoint orbit to this element, mu of P. Okay?
Okay.
And you obtain that actually your moment map is just, well, at some point x is just mu of x minus mu of P. By doing this construction, this direct product. And then you can consider the Marsden-Weinstein reduction with respect to zero locus of this moment map. And this will be the same as to consider the mu minus 1 of P quotient by G here, but fitted into the theory of the Marsden-Weinstein. And this explains, well, okay, I think it requires some time to understand, but I will tell you that this construction, because you need to extend your phase space with the coadjoint orbit, and you need to add some constant Kirillov-Suryo, it means that your phase space now is a big one. You have some Darboux or something on your initial space, plus you add this constant Kirillov-Suryo variables, and when you perform this reduction for the Calogero system, that's why the spin variables, which are actually, well, I told you that they are given by constant Kirillov-Suryo symplectic form, appears in the story, right? So in principle, if you want to consider an arbitrary moment map, you need just to extend your space with the coadjoint orbit of the moment map you choose, and then perform the reduction, but the dimension will be big. But this is
so sorry, but now you have approximately 5 minutes.
yeah, and I'm finishing actually. So well, and that's why, for example, for Calogero Moser, we have a very special recipe which gives you a very non-trivial but small system. In general, you have also non-trivial, not so big but much more bigger systems that the Calogero Moser because of this spin variables, right? And this is the illustration of this story that you start with something big and trivial, then you obtain something small, non-trivial, and if you are lucky enough, you have some special moment maps, moment map value, which gives you even smaller than this one and still non-trivial. Yeah, I guess that's the whole part of my this is the main idea I wanted to explain today. Thank you very much.
Yes, thanks a lot. It was quite interesting. Questions, remarks, comments. No comment? Volodya.
I just wonder now, is it more understandable what Ian Marshall told last time or not?
Well, to be sincere,
Great reaction of other people who attended both talks.
yeah. Well, as for me, it was quite useful to have these two talks next by one. Second, well, Jan's talk was clear, at least half of it was completely clear, and unclearness was in the second part due to technical reasons, to my opinion. But of course, Ilya's talk clarified the picture very much, being quite geometrical. Do you agree? He's not listening. He's doing something else.
He's here. I don't.
He's here, but microphone is switched off.
He's here.
Yeah, he's here. Okay,
because
but
what he told was extremely interesting, especially second half. And when I proposed Ilya to give this talk, which is absolutely, I would say, to initiate this program, just to clarify a little bit second half of Jens' talk.
Yeah, of course, it was very useful. Okay,
Well,
Ilya, thanks a lot. Well, success in your future research, and I hope that it is not the last time we hear you.
Me too. Thank you.
Okay.
I'm happy that I didn't make it worse. So yeah, thanks.
Well, of course, you always can do something worse, but you manage. Thanks. Okay, thanks for attending today's session. So hopefully we shall meet at least one time more this month. You'll be informed about next sessions. Goodbye. Thanks a lot.
Bye-bye.
Thank you, Ilya. My comment was also, I should say that nobody knows, but Ilya has 3 talks this week, and he accepted with this very strong program to give talk. So we should be grateful to him.
I'm honored. Okay. Okay. Goodbye. Thanks.
Bye.
Thank you. Bye.